All right, let's jump right in. We are surrounded by, well, stuff. Your desk, your drink, the very air you're breathing. But how in the world do we make sense of it all? Today we're going to create a little map to help us navigate the material world.
So, let's start with a little riddle, just to get us thinking. You've got invisible air, clear water, and a solid gold ring. I mean, they couldn't seem more different, right? But believe it or not, on a really fundamental level, they share one massive thing in common.
And there it is, the big answer: matter. Everything we can see, feel, and interact with, it's all made of matter. It's the universal stuff that makes up everything from giant galaxies all the way down to a single grain of sand.
Now, just saying, hey, it's all matter, isn't very helpful, especially if you're a scientist trying to figure out how things work. You need a system, right? A way to sort and classify all this stuff. So, where do we even begin?
We start with this map. Now I know, at first glance, it might look a little intense. But don't worry, we're going to break it down step by step. Just think of it as a guide for asking the right questions so you can classify, well, anything.
So the first, most important question is right at the top. When we look at something, the very first decision is this one single pure thing, or is it a bunch of different things all physically jumbled together? This question immediately splits our map into two main paths: pure substances and mixtures.
Let's start by heading down the mixtures path. Why? Honestly, because we see them everywhere in our daily lives, from the food we eat to the air we breathe. This is kind of the messy but really familiar side of our map. And right away, you can see not all mixtures are the same. On the left, you've got cereal. You can clearly see the flakes, maybe some fruit, all the different bits. But on the right, you've got coffee. It's just one uniform liquid. You can't see the water or the coffee grounds or the sugar separately. This visual difference is everything. That bowl of cereal is what scientists call a heterogeneous mixture. The word hetero just means different. It's chunky. You can easily spot all the individual parts. Sand and water, a salad, a pizza. Yep, all classic examples. And that cup of coffee? You guessed it, it's a homogeneous mixture. Homo means same. It's so perfectly uniform, it looks like a single substance. The parts are mixed so well you just can't see them. Things like salt water, the air, even steel. They're all homogeneous mixtures. You might also hear them called solutions. Okay, so that's one whole side of our map explored. Let's backtrack to that first big fork in the road and check out the other path. What happens if what we're looking at isn't a mixture at all? What if it really is just one single pure substance? When we're on the pure substances road, we hit another important question. This time, it's not about physical mixing, it's about chemical bonds. The question is, can we use a chemical reaction to break this substance down into even simpler pieces?
If the answer is yes, we can break it down, then what we have is a compound. A perfect example is water, H2O. It's a pure substance for sure, but you can break it down into hydrogen and oxygen. The key is that those elements are chemically locked together, and a very specific recipe.
Here's a great way to picture it. If elements are like different kinds of Lego bricks, then a compound is a specific thing you build with them. What you're seeing here is a model of iron sulfide. You've got iron atoms, one kind of brick, and sulfur atoms, another kind, chemically clicked together to build one single pure structure.
But what if you can't break it down any further? What if you've hit a chemical wall? Well, then you found an element. This is it. This is the simplest form a pure substance can take. You've hit rock bottom, chemically speaking. So an element is the Lego brick itself. A piece of pure iron is just iron atoms. A chunk of pure carbon is just carbon atoms. These are the absolute fundamental building blocks of all matter, and we have them all organized really neatly on the periodic table. So we figured out how to map matter based on what it's made of. But there's another really useful way to classify things, not by their ingredients, but by their properties. How does it act in the real world? Now, scientists look at all kinds of characteristics, but for now, let's just do a quick fire round on three really common ones you've definitely heard of. Can it conduct electricity? Can it conduct heat? And is it magnetic? These properties are super useful for identifying materials and figuring out what to do with them. First up, electrical conductivity. Does electricity flow through it easily? Materials like copper are fantastic conductors, which is exactly why we use them for everything from those huge power lines to the little charger for your phone. Next, let's talk heat, thermal conductivity. Have you ever left a metal spoon in a cup of hot tea? You know how the handle gets hot really fast? That's because metal transfers heat energy super efficiently.
Great for a cooking pot, maybe not so great for the handle.
And finally, magnetism. This special property, which you find in materials like iron, is a fundamental force that we use all over the place, from giant cranes in scrapyards to the hard drive in your computer.
Phew! Okay, we have covered a lot of ground. We've navigated through mixtures, pure substances, elements, and compounds. We even looked at properties. So let's bring it all back together and turn this knowledge into a practical tool you can actually use.
And here we are, right back where we started, looking at our map. But now, it shouldn't look so intimidating, right? You know the questions to ask. You know what each fork in the road means. This is your personal guide to identifying pretty much anything.
In fact, let's boil it down even more. Here's your simple 3-step toolkit. 1. Is it a mixture or is it pure? 2. If it's a mix, can you see the different parts? And 3. If it's pure, can you break it down with chemistry? That's it. That's the whole game.
So I'll leave you with this final thought, a little challenge. Look around you right now. Pick the closest object, your phone, a glass of water, a wooden pencil, whatever. Try to run it through that toolkit. Using your new map, can you figure out exactly what it is?